This is four languages from 40 years ago, otherwise known as What Can We Learn from the 1970s? And I imagine that most of the people here were born after the 1970s. How many people are under 40? Yeah, almost every. There's a few old people, but most people are under 40, so there you go. A lot of you people weren't even live. So I have this website, F# for Fun and Profit, that is not relevant to this talk. But if you're interested in F#, there you go. So I am old. I have grey hair. I am so old that I was actually alive in the 1970s. That's how old I am. And a few other people will know what I'm talking about. So this is a photo from the 1970s. This is what it used to look like. It was black and white back then too. And that's actually me in the corner. So yeah, it was a long time ago. And for people who were born after that, that seems like ancient history. So here's a quick quiz. How much do you know about the 1970s? How many of you have heard of any of these classic albums, like Led Zeppelin? And yeah, so most people know most of these albums, right? These are kind of pretty famous. So even though they were a long time ago, you know about them. And here's some famous movies from the 1970s, like Jaws and Rocky and Star Wars. Everyone knows Star Wars, Solaris and so on. So most people have heard of these movies, right? How about these 1970s classics? Sequel, ML, the Family Languages, Prologue, and Smalltalk. Now, I'm willing to bet that most of you are not that familiar with these, even though they are classics from the 1970s. So I really think that it's good, to learn about these things, because just like learning about classic music and classic films, you should know about classic programming languages. So one of the reasons is not just to learn for its own sake, but it's actually useful. So if you think about programming or anything, you normally have a toolkit. So if you're doing do-it-yourself or carpentry or something, you have a toolkit, right? You have for hammering nails, you use a hammer. For screwing things in, you use a hammer. For cutting wood, you use a hammer. And for tightening bolts or something, you use a hammer, right? No, of course, nobody would do that. This is silly, right? So what about your programming toolkit? So let's say you're doing domain modeling, you'd use a hammer. And if you're doing complex business rules, you'd use a hammer. And if you're doing data queries, you'd use a hammer. And if you're doing live coding, you'd use a hammer. Now, when it comes to this, like most of us, actually, I do use the same tool for all of these things. And I think that's a problem. I think you should expand your horizons. So expand your toolkit. Learn some new ways of doing things. This is one of my favorite quotes, which is that a language that doesn't affect the way you think about programming is not worth knowing. So, it should change the way you think. And so languages like that, I'm going to give them a galaxy brain seal of approval. This is like, makes your head explode, right? So what kinds of languages do that? Well, the way to expand your toolkit is to learn some of these languages. Now, if you think about the most popular programming languages we have right now, which is Java and JavaScript and C++ and C and C# and Python, here's the problem. These are all the same language. Really, they're kind of dialects of the same language. Learning Java, if you already know C#, learning Java is not going to make your head explode. If you already know Python, Ruby is not going to make your head explode, and Go is not. They're really the same thing. So no galaxy brain if you learn one of these languages. Sorry. I mean, it would be a bit like if I said that I speak 3 languages. I speak British English, and I speak American English, and I speak Australian English. Do I really speak 3 languages? No, I don't really. Right, If you want to, I don't get a galaxy brain for that. If I want to really get a galaxy brain, I need to learn, an African language or an Asian language or a Native American language or something. There's a lot more interesting languages out there than just the ones you're familiar with. So it's a big world. There's lots of places to explore, and I would say let's go out exploring. So what kinds of paradigms do we actually need to know if we want to have a good toolkit for programming? So here's the kind of most important programming paradigms we have. We have the imperative procedural paradigm, which was invented 50 years ago with ALGOL, and really hasn't changed that much since. We have object-oriented programming with Simula in 67 and Smalltalk in 1976 and then later in 1980. We have functional programming, which started in the 1970s with ML. We have symbolic programming, which started with Lisp, and kind of again updated in the 70s with Scheme and so on. We have logic program with Prolog in the 1970s. We have concatenative program as in Forth, also in the 1970s. So what's interesting is the 1970s was a fantastic time for new ideas. All these concepts, most of them originated in the 1970s. All the paradigms we use today. Now, it's true that some of them didn't really emerge full-fledged. It took a while to settle down, but certainly by the mid-80s, everything had sort of stabilized. Small object-oriented programming had stabilized, functional programming had stabilized, and so on. So, that's 35 years ago. So are you caught up with the state of the art from 35 years ago? That's my question to you. You're always on the latest JavaScript framework, but how many people know stuff from, that was the state of the art, and we're still very, very behind, unfortunately, most of us. So let's go back to the 1970s and look at some of these languages. So the first one is SQL from 1974, and it gets a Galaxy brain because it was so radical compared with what people did before. And even today, if you're not familiar with SQL, it can actually definitely change the way you think. So it was part of the first relational database. It was created at the same time. And before SQL, every single database company had their own proprietary APIs. And you had to learn, every time you switched to a different database, you had to learn a whole different API. So, can you imagine if you had to do that today? Let's say you're using, Mongo and Redis and Cassandra and stuff, and you had to learn a different API. That would be terrible, right? So it was a radical change to have a common model that all the database vendors could use. So the first thing we can learn from SQL is that it has a really consistent model. Everything is a set of relations. So it's got a kind of mathematical basis to it. It's set theory. So here's something you're probably familiar with. You've got a table with a person and a table with a parent-child relationship or something. And with SQL, every time you do something, you get another set of relations. So if I do a select, that basically projects a column. But that column is now still a little mini table, right, a little set of relations. So that's consistent. And then if I do some sort of filter, that takes some subset of the rows, and that's also another set of relations. So no matter what you do, you've always got a set. So it's set theory, and it's very consistent. And one of the nice things about being consistent is it's very predictable. So if I say I've got this language and it uses kind of sets of things as its basic fundamental model, you might say, well, that's interesting. You're doing set operations. Do you have a way of doing Cartesian products? Because that's like a pretty standard thing. And you say, sure, yeah, you do. You have outer joins. That's like built into SQL. And inner joins is just an outer join with a filter on it. So, you can predict exactly how everything's going to work if you have the mental model of how it works. Now, the other thing that SQL has, which might not be obvious, is it's composable, because it's an expression-oriented language. So what that means is everything that you do in a SQL query language anyway returns another little set of relations, another set, which means you can take it and embed it as a subquery, and you can take that thing and embed it as another subquery. So you can make bigger things from smaller things. And that is sort of the definition of composability. And that's something we always strive for as programmers. So expression-oriented languages are the way to go if you want composability. Anything to do with procedures or statements where you do something but you don't get anything out the other side, that's not composable. That's really bad. So like Lego, that's composability. You can glue things together. There's another reason why expressions are really nice too. And that's because they eliminate certain kinds of error. They make life easier for you as a programmer. And so obviously this is not SQL, this is a sort of C-like code. And here we have some sort of result int, and it's a Boolean, and if the Boolean is true, the result's set to 42. Okay, so this is a really trivial piece of code. But there's quite a lot of things, even in this trivial piece of code, there's things that can cause problems. And you might not even be aware of the things that can cause problems because you're used to writing code like this for most people. The first problem is that the result variable has to be created before it's used, which means you have to assign it some sort of value. And what value are you going to assign it? Well, you can, in this case, you'll probably give it a 0 or something. If it's a pointer or an object, you're going to give it null. And now you have the dreaded null reference possibility, So that's a problem. And then what happens if I create this result variable, but I forget to assign it? And that just be a bug, right? That's quite a serious bug. And there's nothing stopping me from doing that. And again, if I forget to handle the else case, I mean, there's normally an else case, but so what happens in that case? It's not at all obvious from this code. I might just forget about it. And that has actually caused serious bugs in real production systems. And because there's a side effect, in the sense we've got this kind of, within this scope, the result is kind of out of that scope, it's kind of global relative to that scope. And it means it's really hard to pull this little piece of code out and extract it as a method, because it's got this dependencies on things outside its scope. So in an expression-oriented version, this is the C ternary expression, the result variable is assigned afterwards. It's assigned to the result of the expression, which means you never have to worry about what to assign it. And you can never forget about assigning it, right? So you can't forget, and what you don't have to decide, is it going to be a nil or a null or a zero, because you only assign it when you actually use it. In a ternary expression, you have to have the else case, right? You can't forget to handle the else. And because there's no dependencies outside the scope, you can literally take that little piece of code and copy and paste it into a little new function, So it's much easier to refactor expression-based code than it is to refactor statement-based code. So, this is just really nice. So they reduce bugs and they make refactoring easier. So expression-based languages are really, really nice compared with statement-based languages or procedural languages. So I highly recommend you use one. Most languages that most people use are not expression-based languages, which is kind of interesting. Another thing about SQL is declarative. So that means, you say what you want to do, you don't say how you want to do it. So this is some code, and it's very detailed. It's telling the computer exactly what to do. Open this file and do stuff. But it's very detailed, but it's like, what is this code trying to do? It's not at all obvious. Because the implementation is so mixed up with the goal. Now, if I do the same thing in SQL, it's really obvious what this code is trying to do, because I'm telling what I want to do. I don't tell SQL which file to open. I don't say which indexes to use. I don't say all that stuff. I just give it what I want to do. And one of the nice side effects of doing this is that the performance can be tweaked independently of the logic. So if SQL code is slow for some reason, I can add an index or something, but I don't have to change the logic. In the C-style code, if I wanted to increase the performance of that code, I'd have to basically rewrite the whole thing to use hash tables or something. I mean, I don't know. But, I couldn't just take the logic and tweak it to make it faster. Final thing about about SQL, is the separation of concerns, because it's a query language. Duh. Right? The query language is a query language. There's no updating of tables in there. It's just queries. Now, there's another language, the data manipulation language, which is doing updates and deletes and so on. And there's another language which is for defining tables. Now, commonly, we mean all three things together when we say SQL, but originally, SQL was for queries. And you can't, all it did is queries. It didn't do updates. So it had a separation of concerns. The update language is one thing, and the query language is something else. So what can we learn from SQL? It's got this consistent model. It's predictable. It's composable because it's compression-based. It's got a declarative interface. It's got separation of concerns. We reinvent this. We say, oh, come on, query separation. This is going back to the 1970s. They already knew that, right? This is not a new idea. And finally, kind of interactivity is really nice, because with SQL, you can play with it. You can type an expression and you can run it and see what happens. You don't have to compile it and wait 5 minutes to see what the answer is. I mean, if SQL was like that, it would be really annoying, wouldn't it? It's like the fact you can just play with stuff until you get it right. So experimentation is really important. Sadly, most popular languages are still not expression-based, even though expression-based languages are so awesome. All the ones all the ones I had before, C and Java and Go and all that stuff, they don't use expressions. So sad. Right, next one is Prolog, 1972, a long time ago. It gets a galaxy brain because it'll literally change the way you think if you learn to use it. So the background for Prolog, it was the first mainstream logic programming language in France. It was the kind of European answer to Lisp, with the whole AI thing that happened in the 70s. That kind of died, and just like Lisp, Prolog is just as esoteric. Everyone thought it was going to be the next big thing, but it didn't. but it's still worth learning. So what can we learn from Prolog? Well, it's got a consistent model. Now in Prolog, everything is a fact or a rule. So it's not a set of relations, it's facts and rules. And this is what it looks like. There's some facts. And this kind of looks awfully like a table, pairs of things. But also in Prolog, you can have rules. So for example, to be a grandparent of somebody, you have to be a parent of somebody, and that somebody else has to be the parent of a child. And that makes you a grandparent. Or if person 1 is older than person 2, then person 1 has an age and person 2 has an age, and person 1's age is bigger than person 2's age. So there's a rule. But what's interesting is in Prolog, the rules and the facts, when you use them, you can't tell the difference. They work exactly the same way. So it's not like you have to write stored procs in SQL, And again, it's declarative. You say what you want to do, not how you want to do it. So if I say to Prolog, is it a fact that Liz is 92? And the answer is yes. Okay, true. Now, you can also pass in an unbound variable, and you say, well, who is it who is 92? And it will say Liz is the answer. Or you can say, what is the age of Liz? And it will come back with the answer. So what's kind of nice is that it's bidirectional. Unlike SQL, where I'd have to write 3 different queries, this is it's basically one clause, and I can pass in different things to get different answers. It's really nice. And like I say, rules and facts look the same. So this is actually a rule, but I can't really tell whether this is a rule or a fact when I actually use it. Same thing, this is another rule, it looks like a fact. And again, just like with the facts, I can pass in unbound things, and it will actually give me all the answers. It'll give me multiple answers back, which is kind of nice. And if I pass an unbound thing, it will figure that out. So the basic stuff in Prolog is pretty easy. One thing that Prolog has is this bidirectional unification, which I was talking about. So if I say, what is the list 1 followed by the list 1, 2, 3? And I put it x as the missing parameter, and it'll say, well, x must be 1, 2, 3. That's the list. Okay, well, that's pretty obvious. And then I say, well, what do you have to put in front of 2 and 3 to make 1, 2, 3? So that's the append. And it says, well, x has to be 1. Okay, well, that's pretty obvious. But then you can say things like, how many different ways can you make 1, 2, 3? What are the two? If I have 2 possible things, how can I make 1, 2, 3? And it'll say, well, x could be empty and y could be 1, 2, 3, or x could be 1 and y could be 2 and 3, or x could be 1 and 2 and 3. So it'll give you 4 different answers. So that's really nice. And if you think about this, obviously this is a trivial example, but when you think about more complex examples, this is a lot of power just by doing that, and it's built in. So let me do you a quick demo of Prolog. Where am I? Yeah. So here's the facts I'm using, and here's the rules I'm using. So I can take a fact like this, or a rule like this, and paste it into the console. And it says it's true, and I say, who is Liz the grandparents of, and it will give me multiple answers. So that's just basically what I showed you. But here's a thing that you can actually use to make more powerful stuff. This is a Sudoku solver written in Prolog in 10 lines of code. And I'll just take you don't have to worry exactly how the code works, but I'll just take you through the ideas. So Sudoku, it says there's 9 rows, and each row has the same length. And each row contains a number from 1 to 9, and every number has to be different. And then if you transpose the rows, you get the columns. And again, every number in the columns has to be different. And then if you give the rows names, A, B, C, D, E, F, D, there's some rules about the first 3 rows have to be divided into blocks, and each of those blocks has to be separate. And then the next 3 rows can be divided into blocks, and each of those will be separate. And the third 3 rows are blocks. And within a block, they're all distinct. So that's the rules for Prolog in like 10 lines of Sudoku in 10 lines of code. And this is the definition of a problem here, and I've got little underscores for things I don't know the answer to. So if I say, please solve this problem, Prolog, I go over here, and there's the answer. Okay, so it figured it out just from those rules, which is kind of cool. Now, thank you. It's kind of awesome when you see it, isn't it? Problem number 2 has 2 8s in the same row. So this is not a solvable Sudoku. So if I go to the console and I say, please solve number 2, it says false. There are no answers. Now, if there are multiple solutions, it would give me multiple solutions and so on. Now, of course, you don't normally solve Sudoku in your day job, but there are actually many things which are very similar, which are constraint-based problems. Like you have a bunch of business rules and you have to pick let's say you're doing a pricing engine, you have to pick the price which is the cheapest price. Or if this thing, or kind of an expert system, if this thing is true, this thing has to happen, but this other thing is true, then this other thing has to happen. That's basically constraint-based modeling and programming. So let's go back to the thing here. So what can we learn from Prolog? Again, consistent model, everything's facts and rules. It's declarative. And we never had to, like with the Sudoku, we didn't have to say how to solve. We didn't say, what the implementation was. We just said, this is the rules, and it figured it out. Now, this is not always applicable. I mean, it's not a silver bullet that will solve all problems, but in the problems it does solve, it's really, really good. This kind of unification thing is really cool, that you can do bidirectional figuring out what the variables are. So you can say what's true, what matches, and so on. And again, it's interactive. The whole Sudoku thing, I could just type it and see if it works and play with it a bit. You can experiment. So that kind of interactivity is really important. Now, what's interesting, this is back in the 1970s when people were using terminals, right? They're doing this stuff on mini computers, probably. This is before GUIs, and they were very big on interactivity. So that's, So if you are writing a rules engine, do think about using Prolog. It might make your life a lot easier. Right, third language, which is ML. ML gets a Galaxy brain. It is the first functional programming language, or major one, and it was the parent of modern languages like SML, OCaml, and F#. And so there's the logos for OCaml and F#. It originally started from meta language, and it was part of a theorem proving system. So do not confuse ML with machine learning. It's a completely different thing. It's an impure language. It means you're allowed to have mutation and you're allowed to do I/O and stuff. So it's not like Haskell is a whole kind of slightly different branch of functional programming. But it's really, really pragmatic language. People who use these languages really, really love them. We've seen this before. What can we learn from ML? It's got a consistent model too. They were really big on consistent models in the 70s. They were really trying to come up with basically the opposite of Perl. Like Perl is a kitchen sink language. You just dump everything in. If you need a new feature, you just add it, or Scala or something. It's like, they really wanted to have kind of elegant models that worked throughout the language. So the thing about the reason it's the kind of parent of functional programming language is because functions are just normal things in ML languages. They're just like an int or a bool or a string. You can pass them around as parameters. You can have the output of something be a function. You can have the input be a function. You can put functions in lists and so on and so forth. They're just normal things. You just treat functions as first-class citizens. And that was kind of a big step forward. So I'm not going to be talking about functional programming because other people have already done this talk. So I'm just going to talk about some of the cool things of ML which you might not be aware of. So the first thing about ML, the second thing about ML is the type inference. And type inference uses the same kind of algorithm that we already saw with Prolog. So for people who aren't familiar with type inference, let me just give you a quick little demo. Let's say we have this function, do something, and it's got 2 parameters, an f and an x, and you say x plus 1, and then you run a function on it, and then you get y, and then you add y to hello. So there's your 2 parameters. Now, the original ML from the 1970s isn't around anymore, so this is F# code, but it's really, really similar. The concepts are very, very similar. So, how does the type inference thing work? Well, first of all, it says, well, if you're adding 1 to x, then x must also be an int. Okay, that makes sense. And if you're adding hello to y, then y has to be a string. That makes sense too. And then this function, well, the input to this function is going to be an int, and the output is going to be a string. So this function is an int to string function. So there you go. Everything's inferred. We've got the f parameter is an int to string. the x parameter is an int, and the final result type is a string. So the type inference engine does all this nicely. So this is compiled time. This is compile time. So it looks like a dynamic language like Python or something, but it is actually just as statically checked as C# or Java. So that's nice, but there's another reason why type inference is really good, and that's this kind of code. This is from C#. This is the link group by method. And you see there's a lot of duplication. It's an I enumerable which returns an I grouping of a T of resources. Like, you can get really lost looking at this code, and if you were writing your own code, trying to figure this out would be quite complicated. Now the F# code looks like this, without all that stuff. Now it compiles to exactly the same code. I mean, the F# figures all this stuff out for you. So from my point of view, one of the benefits of type inference is just like less typing. I don't have to type all that stuff, which is nice. But I think the real benefit is there's less noise, right? It's less. You can really focus on the logic. The C# code is really noisy with all those type parameters. So it's really hard to figure out. You can't even hardly figure out what the name of the method is because it's kind of buried in there. Another thing about ML family languages, they have sensible defaults. So you get immutability by default. If you want mutability, you have to ask for it. It's a special case, which is the opposite of most other languages. Everything's non-nullable by default. I mean, if you want nullability, you can ask for it, but it's a special case. You get structural equality by default. So if you have two things and they have the same data in them, they're going to compare equal by default. If you want reference equality, comparing their pointers, that's something different. You have to ask for it. Now, again, that's completely opposite. In OO languages, you get reference equality by default, and if you want to do something, you have to override equals. You have to override equals and override get hash code, and that's really annoying. So this is a much nicer default, I think. And in ML languages, everything has to be initialized. So you can't ever have like a null, because in that example with the statement-based thing, you had to have the return value had to be initialized to something, so you have to set it to null or 0 or something. ML is expression-based. So you always initialize things at the end, and so you don't have nulls being passed around. And the final thing about ML, which you've seen in my other talks I'm going to go on about a lot, is it has an algebraic type system, which I prefer to call a composable type system, which means you glue types together to make bigger types, just like you can glue other things, just like Lego again. And that's only possible because the behavior and the data are separate in a functional language. In OO language, you couldn't do this. Technically, just to be clear, this is not part of the original ML from the 1970s. It got moved into in the late 70s and early 80s. So it's only 35 years old. It's not really 40 years old. So sorry about that. Right, so here's how you build new types. For people who haven't seen this, hopefully this is interesting. For people who have seen this, I'm sorry, I'm going to say it again. But here we go. You can AND things together and you can OR things together. And I'll give you some examples. So ANDing things together means, to make a fruit salad, I have an apple and a banana and a cherry. And this is what it looks like in F# or an ML language. And this is a record type. This is a struct or a record or whatever. This is, everyone's familiar with this. All languages have something like this. But the other thing that the ML languages have is composing with OR. And that's, let's say you want a snack, and it's an apple or a banana or a cherry. So it's one of them. It's not all three at the same time. You have to pick one. And this is the kind of thing that's not available in most mainstream languages. And in F# you'd write like this, with a vertical bar, meaning OR. And so an apple, it can be an apple or a banana. If it is an apple, it has to be one of the apple varieties. And if it's a banana, it has to be one of the banana varieties. But it's not all three at the same time. So I call these choice types, also known as sum types, also known as discriminated unions, and so on. So they're really, really useful in the real world. And I'll give you an example. Let's say you're trying to do some sort of payment system, and we have cash, check, and credit card. Well, nobody really takes check anymore. So this is an example from the 1970s. Because, nobody takes cash anymore either. So what you do, in an OO system, you might start with defining some interfaces, and you might inherit from the interfaces or something. In an algebraic system or composable system, you build up from the bottom. So you start off with some primitive types like card number and check number and so on. And then you take those and you use them in a bigger system. So you might say, well, a card type is a choice between a Visa and a MasterCard, and a credit card information is a card type and a card number. So we've got a choice type and we've got an and type. And then to make the payment method, we might say, okay, it's cash, or it's a check, or it's a card. If it's a check, we have this extra information, which is the check number. And if it's a card, we have this extra information, which is a credit card. So again, that's a choice. But we can keep going. We can say, okay, let's do some more primitives. The payment amount, currency is a euro or dollars. So another primitive type, another choice type. And we can keep going and going, and we can like make a big one. Finally, the big payment thing is an amount and a currency and a payment method. So we've built quite a complex system, and that last one is a record. We've built a big system from smaller types. We've been building and building this, again, the Lego analogy. And what's cool is it's executable documentation. If I show you this code, you can pretty much figure out, you don't exactly know how it works, but you can figure out what's going on just by looking at the names. So you've got nouns, and you can also do verbs in functional programming, because it's just functions. So to deal or to pick up a card, here's how you do it. So that's the entire domain on one screen, which is really useful if you're doing domain-driven design. So anyone doing domain-driven design really needs to look into a language with algebraic types like this. And what's also cool is even if you're not a programmer, you can look at this code and sort of understand it. So if I say to a business analyst, what payment methods are accepted, or they ask me, I say, here's the code, you guess. And they can probably make a good guess. They don't have to look in 20 different files to figure it out. It's all in one place. So this is a huge topic. I have a whole bunch of talks on this, and I have a whole book on this. So if you're interested, come and ask me afterwards. I could do an ML demo here, but I'm not going to because I haven't got enough time. Next, I've got to learn from ML. Consistent model. I'm going to sound like a broken record, right? Consistent model, expression-based. It's got type inference, which is awesome. It's got sensible defaults, and it's got algebraic types, which are also awesome. And what's sad is the Java developers only just got var, right? Now, type inference has been around for 40 years. And it's still kind of new to people. I think that's kind of sad. And algebraic types have been around for 35 years. And I think they're absolutely essential if you're doing any kind of domain modeling. And again, most languages don't have them. So really, we've forgotten a lot of stuff which is really valuable from a long time ago. Right, onto my favorite language, which is Smalltalk. 1976, there's actually 3 versions, 1972, 1976, and 1980. The 1981 was sort of the most stable one. But I'm going to put 1976 in just because it's the middle of the 70s. Galaxy Brain, it gets many, many, many Galaxy Brains. One of the most influential languages, along with Lisp and Algol, probably the most influential language ever written. I really love Smalltalk. It was one of my first programming languages, and I still love it to bits. When Smalltalk was around, people were using teletypes like this. And the sad thing is, we're still using teletypes. And you're using a console, a TTY console. You're writing an emulator for something from the 1950s. Is this really the best way you can program? Right? Using a teletype, is it really the best way you could program? So Smalltalk was developed at Xerox PARC. Xerox PARC was amazing if you don't know them. They also did the first PC, the first GUI, the first laser printer, the Ethernet, etc., etc. All came out of Xerox PARC, PostScript, and so on. Smalltalk alone introduced a lot of new programming stuff, introduced message-based, object-oriented programming. It introduced model view controller. It had a windowing IDE. It had a virtual machine. It had a generational garbage collector. This is all back in the 1970s. And what's interesting, it gets many, 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 many Galaxy Brains. What's interesting is most of the agile thought leaders, people like Martin Fowler and Kent Beck and stuff, are all ex-Smalltalkers. So if you want to be an agile thought leader, go and learn Smalltalk, because it will make you. Seriously, I actually do think one of the reasons why it was good is because these people had this experience with Smalltalk. This is the user interface from the early 80s. It's on a Mac. What's interesting is this is 35 years ago, and it still hasn't changed very much. So IDEs, all the IDEs use are based on Smalltalk. So what can we learn from Smalltalk? It's got a consistent model. Everything's an object. Everything's an object. Everything's an object. Everything's an object. And really, really, everything is an object. I cannot stress this enough. It's got minimal syntax. This is something that it doesn't really get talked about enough, but the whole syntax fits on a postcard, unlike certain languages where it's like a 1,000-page book. And one of the things they do is they put the power in the language. Rather than having features, they put the power in the language, so all sorts of features can be done without changing the language. And that's also part of the Lisp philosophy, if you're a Lisper too. I mean, a good example, which is not really Smalltalk related, but in recently, a lot of languages have got async. In C#, async is implemented as a new language feature, which requires a new compiler. In F#, async is just a library. You don't have to change the language. So you can add new features without changing anything. So that's kind of cool. And I'll give you a demonstration of that when I do the demo. Another thing about Smalltalk is late binding, which means that you're going to be really dynamic. You can do things up to the last minute because you're passing messages. You can change the code at all points. And I'm just going to have to do a demo to explain all this stuff because there's no way I can even talk about it. And finally, text files. Smalltalk doesn't use text files. So how can you even program without text files? All right, so everything's in memory all the time in Smalltalk. Right, I've got to do a Smalltalk demo now. And where am I? Here we go. So here is Smalltalk. This is a Smalltalk interaction thing. There's basically three kinds of messages. You can send a unary message, and there's the answer, which is hex. This is a Smalltalk version of hex 2a. You can have binary messages, 43. And if you have parameters, you use colons. So 42 raised to 2 is 7064. And what's interesting is that these, it always spits the answer out in the same place. So, I mean, I can then continue to use that answer, interactively like that. And if I don't want it, I can just normally, it's already highlighted. So if I just don't want it, I just hit backspace and it's gone. So that's the entire Smalltalk syntax right there, pretty much. So that's everything you need to know about Smalltalk. Right. Now, one of the things in most programming languages, you have to watch out for bad things. So if I do 42 raised to 100, that's going to be a really large number, so just watch it crash. Okay, so it didn't crash. And the reason is that Smalltalk was designed to be really, really user-friendly. Don't make me think. Why do I care about the size of ints, whether it's an int 16 or int 32, all that stuff? Why do I care? If I want to do 100 factorial, I get 100 factorial. It's like, it's designed to, it's hiding the computer. As a user, I don't care about the hardware. This is a very different philosophy, especially in the 70s. It's like opposed with the C philosophy, where you really care about the hardware. Smalltalk is like, care about the user more than hardware. The user is the person who's using the program. So, I mean, here's a good example. What's a half plus a third? And the answer, whoops, that's not the answer. The answer is 5/6. Right. So, Smalltalk does fractions, it does all this stuff, does large integers. You never have to worry about, doing the wrong thing. It tries to do the right thing. All right, let's look at late binding. So this is a message, and this is the target of the message. So if I say hello, integers are objects. Everything's an object. So I'm going to say to the integer, please do this. Here's the message. Say hello. And when I run it, it's going to say, I do not understand hello from NewCrafts. Now, that's a compiler error, but it's not a compiler error in Smalltalk. Because what I do is I go into the debugger. There's the actual error. It goes straight to the source code. And I'm going to say, hello from NewCrafts. Whoops. I'm going to save it. And I'm going to keep going with the debugger, and there's the answer. So this thing is, you're basically writing code in the debugger. You just write code, even if it doesn't work, and you execute it, and you find out which bits don't work, and you fix it up, and then you keep going, and you run another bit, and you fix it up. You basically can write in the debugger. You can change code at the last minute. And the other thing is, where did I put that new method? Which file did I put it in? right? I didn't put it anywhere. I mean, that method's still there. It didn't disappear. I can run it again. But I didn't have to worry about, again, don't burden me with details that's not relevant to programming. Saving files and all that stuff, that's not part of programming. Right, so here's this 35-year-old IDE. So you can do, everything is objects, like I say, and you can do things like browse. So this is the small integer class, which is a subclass of integer, which is a subclass of number, and so on. So you've got this nice class browser. You can see all the methods that are supported on integers and so on. You've got nice grouping. You can do searching. I can say, where is the hello from NewCrafts? There it is. Here's where the definition is. Here's the references to it. This is all in the very first thing going back to the 1980s. Right. So this is a really powerful IDE. And you can also inspect individual things. If I inspect this, there's the actual value there. And if you have like more complicated something, this is a global object. If I inspect it, whoops, I get this little kind of window that pops up, and it tells me what the instance variables are and so on. I can drill in. And this is built in, again, this is built into Smalltalk, and you can actually write your own custom inspectors and so on. Very, very cool, 35 years old, good. Right, everything's an object. So if I say, what is the class of 42? It says small integer. Now in Smalltalk, that's an object, okay? So I can say, small integer, what is your class? And it will say, my class is small integer class, which is the class of small integers. Okay, what's the class of that? Well, it's class metaclass. What's the class of that? Metaclass class. What is the class of that? And the answer is metaclass. So you actually have a loop. It's one of the few places you have a loop between metaclass and class. But there's no distinction. Classes are objects. There's no static methods. There is methods that instances have and methods that the class object has. And there's a method class for the class, and they have methods too. So there's no distinction between classes and instances. So how do you create a new instance? There's no constructors in Smalltalk, right? How do you send it? You create a message. So here's my animal class, and here's a message. It creates a new animal. So I create another animal. So there's no constructors in Smalltalk. How do I create a new class? Right? So this, if you look at a class like animal, you see down here, this kind of looks like a definition, but it's actually not, it's a message. So if I want to create a class called animal2, I can literally just save that, and you see that animal2 popped up? So to create animal2, I just send a message to object, because object's another thing. So everything's messages. There's no, to create a new animal2, there's no special constructor syntax, I just send it a message. And finally, I'm just running a little bit late here. In Smalltalk, there's no special syntax in general. There's no if statements, there's no for loops, there's no switch statement, there's no constructors, etc., etc. So how do you do stuff in Smalltalk? How do you write conditional code? So here's some conditional code in Smalltalk. And if 1 equals 1, if it's true, do this, and if it's false, do this. Right? And that works. But what's going on here? You can probably see this is actually a message. So what I'm doing is I'm sending a Boolean a message, and the message is, if it's true, do this thing, and if it's false, do that thing. Right? There's no special syntax. There's no special syntax for loops or anything like that. So if I look at the implementation for if true, it says there are 3 implementations. One of them is on Boolean, and the Boolean one says, subclass responsibility, it's not my problem. And there's 2 subclasses of Boolean called true and false. Now the true class implements it one way, and it implements it by executing that block, which is like passing in a lambda. And the false class implements it the other way by executing the false block. So if you used lambda calculus, this is basically lambda calculus in Smalltalk. So that's how you do all the stuff. Like if you're looping over a collection, you pass in a block to do stuff. So there you go. That's pretty much everything I want to say about Smalltalk. So it's definitely worth checking out. It's really, really cool language. I just really touched the surface of it. So just a couple more minutes. So what can we learn from Smalltalk? Consistent model, again, everything's an object. Minimizing the syntax, right? The language is so powerful that I could write if true, I could write, I didn't need constructors, I didn't need if true and false because the language was designed to be powerful. And finally is be awesome and make people fall in love with you. Everyone who's used Smalltalk kind of falls in love with it. And one of the things that a lot of the people in the 70s and the early 80s did, like with the first Mac and so on, they spent a lot of time trying to make people fall in love with it. And they spent a lot of time on the icons on the Mac, and the Smalltalk people spent a lot of time trying to make it really, really easy to use. And I think that's something we've sort of forgotten about. We tend to be very kind of practical focused. It's like just get it done. Making people fall in love with you is actually a really nice thing to do. So do spend some effort doing that. Right, so just to finish up, what can we learn from the 70s? Many, many great ideas were done 40 years ago, and we've sort of forgotten about them, which is kind of sad. They really should be more widely known, and that's one of the reasons why I'm doing this talk. And also, there are many, so just from the historical point of view, but also from the practical point of view, when you're solving problems, there are lots of different ways to solve problems. It's good to have a big toolbox. If you're doing live coding, Smalltalk is fantastic. If you're doing query languages, doing data queries, SQL is fantastic. If you're doing rules stuff, then Prolog is fantastic. Or if you're doing domain modeling, algebraic types are fantastic. So use the right tool for the job. Do not always use hammers. You also have wrenches. You also have screwdrivers. Learn about these other tools and use them. One more thing. It's just one of my little pet peeves. None of these languages use C-style syntax. There are no curly braces anywhere, right? Everyone thinks that languages have to have curly braces. That's not true. In those days, people knew their grammar. When they had a sentence, they ended it properly with a period, not a semicolon. If you went to your school teacher would be really annoyed with you if you ended sentences with a semicolon. So both Prolog and Smalltalk use periods to end things. And there's no dot syntax, right? Smalltalk is like the ultimate OO language, and it doesn't use dot syntax. So just expand your brain, learn some other syntaxes too. So a language that doesn't affect the way you think about programming is not worth knowing. That's my original thing. So go forth, expand your galaxy brain, and learn some new tools. So I'll put this talk up on my website at 4 from 40, and if you like my books, there they are. People seem to like this book. I think it's upstairs in the bookshop. I'm happy to sign it, by the way, if anyone has a copy. You can @ me on Twitter, and thank you very much. And come and grab me for questions. I'm around. Cheers.